Um, this is Dan. I'm going to do a little programming video here, um, sort of to follow up on a couple of topics. Um, I'm not sure how long this will take, but hoping within an hour. I'm going to be, the idea was to cover a few different related things, being those being arrays, pointers, and data structures. Well, structs, which are a form of data structures. And those can all be used to um, store or refer to data that you can then modify or play around with. Um, so, what? Why don't we get going, shall we? Just gonna make sure I got this up here. And okay, so I'm going to program in C. That's a preferred language of mine, um, and it is. It can be very. Sorry about that. It can be very dangerous in a sense. Actually, sometimes literally, it can be dangerous to. It can be dangerous to play around with it if you don't know exactly what you're doing. Um, Typically, these days, modern operating systems tend to clean up some of the messes that might occur, but you still want to take care when you're, especially when you're playing around with the aforementioned pointers. I'll explain what those are in due time. So let's start out with arrays. Um, so arrays are variables that hold not just one piece of data. An array can hold multiple pieces of data. So let's declare an array inside our main function here. So let's go with a character array, sometimes referred to as a string of characters. So declare a character type, because that's what we want. And then we'll call it name, let's say. Give it a maximum of, oh, I don't know, say 25. So now we've got our name. Now we can initialize it, and I'm not sure how many names I can think of that are 25 characters long, but let's just use mine for the sake of it. Oh, I want to use single quotes in C. There is a distinction between single and double quotes for characters and strings. All right, so now we have our name array, our character array, initialized to my name, just because I guess I like myself that much. No, I'm kidding. But now we can print that out, and we can show. Whoops. Compile. Oh, I see what happened. There we go. Sorry about that. I typed includes instead of include. Shame on me. So now, voila, we have created a name array. We've assigned it a value, or a series of values, technically, and we printed the contents of the array out. Now, what if we wanted to keep it open to modification? Let's say prompt the user for input. Oops. Sorry about all the little tones if you're hearing them. So what we can do then is to say print out a prompt, enter your name. And then we can use a function called fgetS, and that takes, I believe, 3 different parameters. We take the name of the variable, the array in this case, and then we take the number of characters, or however long it is, the number of bytes. Since it's character, it's going to be 1 byte per unit. So because we have 25 of those units of characters types, it's going to be 25 bytes. So if we wanted to be hasty, we could just type in 25. A better way to do it is to include some string processing functions here and make sure we include the length of the string, whatever that may be. In this case, name. And then we type in how to enter the thing from which we're going to derive the input. stdin is a placeholder for standard input, in which case refers to the keyboard, and that will hopefully take our name and print it back out. So let's compile. No errors on compile so far. Okay. So enter your name. Interesting in that it did not prompt me. Well, it prompted rather, but it did not pause to. It did not pause to allow me to input. So I changed the string length back to 25 as a literal integer. Let's see what happens. Okay. Well, let's try this then. I'll pick a name. Something from Latin class, I remember. Cornelius. Sorry for you people who... sorry for any of you folks who were traumatized by Latin class. But anyway, so I'll type in Cornelius. And we print back out Cornelius. Now note that there is an extra line between the name printout and the command prompt. The reason for that is that along with the letters that I'm inputting into the character array, it's also taking the new line character from the enter key that's being input, and it's treating that as its own character. So there is a way we can modify the behavior of the program to change that. This is possibly not the best way, but let's go to a line here, and I'll just make up a variable. Well, that's less than string length of the name. We can make sure if the particular element or particular element in the array is equal to the new line character, then we can say that character should in fact be a null string terminator. That's a fancy word for saying that's the end of the line, or a fancy term for saying that's the end of the line. All right, so we've got our little loop here that'll take care of that. Now let's compile, and of course I created a new variable, but I wrote it in, but I did not instantiate it. Little silly mistakes like that. So I can do that. Set it to 0 as a baseline, and okay. Oops. And I think I forgot a parentheses. I did. Make sure you count your parentheses, folks. All right. So now we enter our name, Cornelius, just because for old time's sake. And now, interesting behavior. What did I forget? I forgot to increment the value of the index. Silly mistakes all around. It's late. I'll blame it on that. Okay, there we go. So we took our name. It doesn't matter what it is, but in this case Cornelius. We sought the new line character and replaced it with the the null termination string, null termination character, and we printed the result of that to the screen. Great. Okay, so we've handled character arrays with input from numerical arrays. That is a little different. That is something I'll show here. So we've already got our I variable here. I will create I'll create a character called an array called int array. Sure, why not? And I'll make it the same. So we can populate this, at least with a couple different values. Or we can initialize all these to 0. That's an easy way to say, let's make all of these elements in the array 0. Now if we do this, and then if we try this same printing with the integer array, I bet you we will come across a warning or an error. Surprisingly to me, we did not. So let's try to run it. All right, so let's change it to Foxtrot. Sure. Okay. So we have what appears to be blank, where we expect the printout of the integer array. The reason for that is the placeholder, which is the %s in this case, designates that the printout is expecting a string of characters. And 0 as a number is representative of null, which is pretty much nothing. So really, what would be advisable if you wanted to say print out some characters, you could say 67. Let's see, 97, I believe it is, or 93. Okay. So I'll call it 106. 109. 105. Let's see. 101. 709. I think I missed some of that up here. Anyway, let's see. That actually should be. Anyway, you get the idea. Put in some numbers into an array. We initialize at least some of it. And now, compile. That's interesting. But we did get the first letter, which is good. But let's try that. From integer pointer to integer of different size. Ah, yes, right. It's only printing out the first character of the string. That's weird. Okay, so one way to get at the contents of the array is to create another loop. I'll create that after here. I'll just set I to 0 again. And while I is smaller than the size of int array, now those parentheses are typically not required unless you're trying to get the size of a type as opposed to a variable name. Though I find it just much more convenient and consistent to wrap parentheses around. But that's just my take. Other people might have differences in opinion on that. But now let's say we want to print out the contents of that array. Why don't we just do a new line for each element? And we say int array with the index of, or the current index for the array that it's on. Okay, and then we want to make sure to increment, and there you go. And put in prox out again. Well, that's great. So we know that we're getting some sort of value, or values. As it turns out, we are, oh wait, so why don't we do size of int array at the bottom? Why don't we print out what the actual outcome of that is? Because I think I have the wrong operator there. So let's see. Size of usually outputs in what's called an unsigned long, which is another character type. Unsigned simply means that there's no negative value possible for that type of variable. Sure, doesn't really matter at that point. So that's why. If we take a look at the lowermost left corner next to my username here, 100 inexplicably to me is the size of the int array. Oh no, wait. Okay, I know why. So int array is 25, has 25 elements. That's not a problem. The problem is the elements are 4 bytes in size each. So 25 times 4 returns 100. So size of int array will continue counting long past the number of actual integers in our actual array. So what we want to do to protect against any sort of overruns in output is to divide by 4. We can also do size of int. Math. It's lovely. And there you have it. We've got our integers, plus the uninitialized ones, or rather the initialized to 0 ones. 67, 106, 109, 105, 101, and so on and so forth. So we've got our contents of the arrays. Now how about we instead print characters for them. And we take out the new lines, except we create our new line here. What do you think will happen? I'll give you a few moments. Okay, so each of these values that you see here belongs to a set of characters known as the ASCII character set. American Standards of Computational, I forget what the actual acronym is, expanded, but there are certain values that will give you the character representations of these numbers. Typically, the capital letters in the English alphabet starts at number 65 and up. The lowercase letters start, I believe, at 93 or 97. Excuse me a moment. Just need to take care of something here. And so here we are. So what will happen, at least for these first 6 numbers here, in place of that, we'll see letters from the English alphabet printed out on screen. With the zeros, those are all going to be effectively blank. But anyway, let's run the program and see what this all is all about. So enter name. So I pretty much printed out what amounts to gibberish, CJMLEM or CJMIEM, something like that. Doesn't stand for anything. I just put in some numbers that I thought might turn up to be the first 2 letters of Cornelius, but I was off. Regardless, it's clear you can do something called casting, which is not unique to arrays. You can do that to any variable, sometimes with disastrous results, depending on what the casting is, from, say, in this case, integer to a character variable. So yeah. Now, these are what I would refer to as either static or, maybe less confusingly, fixed arrays, which means that they have a specified number of elements, say in this case 25 for both of these. And that's fine. There's nothing wrong with that by itself, except when you think about certain use cases where that may not necessarily be desirable. So we go to pointers. Let's keep name, and instead I will call this name array, and I'll create another one. It'll look somewhat similar. Name pointer. And it's a safe practice to assign it by default or by initialize it with a value of null. The reason being is when the pointer variable instantiates without that initialization, it will point to another memory location, whatever the operating system provides it. Could be non-writable memory, could be non-readable memory, could be something else. And if you're not taking caution to initialize it to something that is safer to have it pointing to than not, then you might run into some undefined behavior or some other sort of issues that could cause the program to crash. And that's something you want to avoid. Nevertheless, we've declared and initialized our name pointer variable, or pointer to a character type. And what we should do, because we want to be good programmers, we want to allocate some memory. How much? Well, we don't know. So before I do that, however, I want to make sure I include the correct library here. stdlib, which includes memory allocation functions like malloc, realloc, and calloc, all of which have their own features of sorts. But let's start with malloc. So I will try to be protective here. So I'm going to write some code which may not necessarily make sense at first, but I'll explain as I move along. Okay. So with this, we've pointed our instantiation of name pointer to null. And what this says, if we're reading from the right part first, that we're trying to allocate some memory. It's going to be 1 times the size of a character type, which is going to be 1 byte. It's always good practice, I think, to have it written out this way, because that will leave less room for assumption, as opposed to having it a size of char. We could have wanted to have more than that. Not that the number of characters would be unknown, or number of bytes to reserve, rather. But it's clearer just to say 1 times that particular unit. So the value that returns from malloc, if it's been successful, is a memory address, which is then assigned to name pointer. However, if it tries to allocate that memory and for whatever reason it can't and returns null as a result, then we get an error and get out of the program. So that is all there just to protect ourselves. And we always want to make sure to free the memory once we're done using it. And actually, now that I think about it, it's always good to, after we free it, to assign the value of null to the pointer variable, because I just figure it's safe to do that rather than having it still pointing at some other piece of memory for exploitation purposes by accident or what have you. So after all that's been written, let's do something with that memory. So instead, because 1 character is not a lot for a name, let's see, how many mono-character mononyms do I know? I don't think I know any off the top of my head. So instead of 1, let's reserve 25 to be consistent with our name array. So we're going to tell the computer basically to reserve 25 bytes of memory, and that memory will be available as long as the memory is not freed. That brings me to another actual point here. So as long as the program is running, even technically beyond the duration of the program. If I don't include the free function, that memory will still technically be considered as allocated, which, without the benefit of a modern operating system like Windows or Mac OS, will cause a memory leak, and that memory will be non-usable, or you might run into issues trying to access or change that memory. So it's always good to have the free in there. And make sure you're freeing the correct address. Because sometimes, going a little further advanced here, if you are doing pointer arithmetic and changing the address that your pointer variable is pointing to without going back to the original address, and then you try to free that, you're going to run into problems. So in fact, why don't I do that right now? I'm going to cause a problem intentionally just to show you what'll happen. So I'll play. So I'll play with my pointer here. I will increment the pointer value by 1, which will not increment the value stored in the address it's pointing to. It will increment the address that it's pointing to by 1 unit, by 1 byte in this case. Okay. May have made a silly mistake because I forgot to put the 25 in there. There we go. All right. Free called on pointer with non-zero offset. Right. So that is a warning describing exactly the problem that I've mentioned. Because we incremented our pointer, the compiler was nice enough to warn us, hey, you're not freeing the same address that you told us you assigned to that. So, regardless, I'm going to go ahead and run that program because it did compile. Free invalid pointer. There you go. Lo and behold. So, we can either, if we need to, for any reason, change the pointer. There are a couple of different things we can do. We can try to decrement the pointer back to where it was before. That, I feel like, is a bit more dangerous because of reasons I've encountered where operations didn't quite go as expected, and then things kind of broke down. But it works. Another thing that can be done is to create a temporary pointer, and then we assign the value of name pointer, to temp. And then instead of name pointer here, we can increment, and then we don't even have to do a decrement with the temp pointer because name pointer is the one that we allocated to. We stored that address. And actually, just to be safe again, before I forget, also probably want to assign null to the temp pointer as well. And there you go. Now, what is contained in those pointers? Whatever address that those pointers are pointing to, but then how do you get to the data that is contained at those faraway addresses? Well, I don't know how far away they are, but here's our pointer variable. Here is the address that pointer is pointing to, which holds some kind of data inside it. So let's do this. I am going to do a couple of printouts. So we got to output the memory address here, and tab, memory address. Oops, and then we're going to do the line. And we're going to do name, pointer, oops, and temp. And similarly, we're going to do that here. Cool. All right. So now, let's say we want to have some sort of character that is in a variable. Let's call it charvar. Well, sounds like a particular pocket monster type thing. Let's call it x. So let's assign it the value of x. Okay. So that'll demonstrate what the difference is between those two pointer addresses. We can also further that along. I'm doing a couple of different ideas at once, so bear with me, I'm sorry. So temp minus name pointer equals, and then whatever the value is there. Actually, it's going to be resolved easily to an integer, so I will do that. And now I'll say temp now assigned to address of charvar. Okay, so now we want to say, oops, actually, I'll assign it behind the scenes here, equals the address. So we use ampersand to designate address of a variable, charvar. So now temp holds the address that points to charvar. And then to get to that data, we dereference the pointer. Dereferencing is done kind of like you're instantiating it with an asterisk preceding. So that's what that is. And now print, and because that's a character value, let's do %c, and then we want to make sure that it takes in asterisk temp. So that will print out our character of x. Should print out x. Assigns address of charvar to pointer temp. Okay. Actually, oops. Calculate difference between temp and name pointer. Okay. Before temp increment, after temp increment. All right. Now, short of any silly mistakes, which I'm sure I have a dozen of them here. Let's see if this compiles. I'm impressed. All right, so let's print out. So I should have printed some other verbiage above to indicate which one is which. But so you see, this is name pointer, and this column is temp, or for these two rows here. So you see temp, name pointer and temp are the same initially. Then I increment temp, and name pointer is still at its original address, which is this long hexadecimal thing, and you see that it's increased by 1 byte. So the difference between temp and name pointer is 1. Temp, after which I assigned temp the value of the address of charvar, and then I printed out the dereferenced temp variable, which gives us x, the letter x. And so that's all important to know when you start to think about how you can use pointers to your advantage in going to different places in memory, recording values or structures of values, writing them to disk, making copies of those, or having multiple pointers pointing to the same thing when you need to. But you have to make sure to keep track of all of those things very carefully. And this is why testing is important. I don't have the environment set up for that, unfortunately, here, for testing specifically. But as far as what I would like to show in terms of arrays and pointers, we've covered some of that. Now, this is more of a cursory glance at these things and some of the things that can be done with those concepts. This certainly isn't exhaustive. I didn't intend for it to be exhaustive. But I did mention structs or data structures earlier, so that will be the last thing I do. And so let's create a struct. Let's imagine we're playing a very simple game. Now, I'm going to, actually, you know what? I'm going to, I'll have to write that all out again. That's okay. That's fine. So, let's imagine we want to build this extremely simple, great or not, game. Now, there are a lot of variables that could go into it, but one of the first things that you might be asked as a player is, what's your name? Or what is your character's name? And what are certain attributes that are generated for your character? Doesn't have to be anything beyond health level. And you're just moving around, and you might have some commands that you type in that allows it to allows your character to navigate in the world in whatever way that takes shape. For now, I'm just, to keep it simple, I am going to focus on sort of like a player structure. So I'm going to make one up. So I'll call it struct player. That's the name. That's how you declare the struct, and it's more like a template for when you actually instantiate it in the program. So the two things I mentioned, let's make it character name, and let's give it 25 characters. I don't know, I like the number 25, I guess. And let's call the second variable health, because you want to make sure you're a healthy character, or you want to make sure you're monitoring your health, if you can. All right, so now the way to declare it in the main program, to instantiate it, is to call struct player and then the name of the variable itself, which let's call P1. Nice and easy. So we can leave it as is, or we can assign values to it. Let's call it, I don't know, Gordian. Gordian not, I guess. And health, let's call it 100. Okay, we've declared our struct, and we've initialized it with those two values. How do we print it out? Well, there's a certain notation that occurs. So print a string and print a decimal value. It's a sort of a dot notation. So we take the variable name dot, p1, dot name, and p1 dot health. Okay, we can compile. Oh. Okay. And function main 11. P1 undeclared. Oops. Oh. Right. So the mistake number 356,225,734. Make sure you assign with the assignment operator, which is in fact equals. Alright, so this should be fine. We've initialized our values. We're going to print them out. And there we have it. Okay. So now, here's where things can get kind of funky. So let's call this struct player star p. Remember what I told you about dynamic arrays? You can have arrays of structs. And let's say, this is probably not the best way to go about it, but let's say we want to allocate some memory to it haphazardly. P equals malloc, and let's create 100 instances of these player P structs, which is not necessarily unheard of, I guess, but all unique. Now, we use size of struct player, I believe. And if the allocation doesn't work out, we print out our error message. Okay. So the fact that nothing happened is actually good, or at least so I would assume. Now, one thing I forgot to do was free. And I'll create a temporary variable, and assign that to p. So the address is going to point to, temp is going to point to the same address as p. And now we can say while I is less than 100, I'm going to declare I up there before I forget. Int I equals 0. Printf. Now, printf character fading a little bit here. There we go. Send 101, and I will make I equal to 1 instead. Okay, so now enter name for character. Okay. And now let's say p.name. Okay. Without doing any error checking, which will take a long while, but let's assume, for the sake of this, that we are going to go with it as is. Now printf, enter, well, actually, you know what? I'm just going to assign everyone to a health of 100. Temp.name, oops, temp.health, health equals 100. Okay. Temp. Okay. Now we increment by 1. Printf. And I'll, just for giggles, I will print out the address of the temp variable. Okay. And you know what? Actually, just to keep it sane, I'm going to allocate 3, because otherwise I'll be here all night. As much as I like doing this, I don't want to bore anyone here. So let's see, character of, that's going to be 3. Okay. Now, given all the editing I just did, I'm not going to be surprised if I come up with compiling errors. Ah, yes. Okay, that is right. So, given that previously we had, I'm just going to make one up here called struct_t, and we just had it as a plain old struct variable as opposed to a pointer to a struct type. We just needed to access the name and the health variables by doing, by doing this. It's not the proper way to do a string assignment, but there we go. All right, so, and then you just do that. That does not work here. There is a different notation that needs to take place. And that is arrow notation, which is minus and then greater than. There we go. All right. All right. Now we do this. Now guess what? There are a couple of things I forgot to do. Without the I incrementing up to a the value of 4, temp will keep on incrementing and printing out until the cows come out, or until I stop the program. So let's see. I also want to make sure that I, in fact, get the I actually get the input going to take input from the keyboard to assign to the current temp name variable. So now, let's see. Could call this, what do we call it? 25. And then stdin. Okay. Okay, that should be it. Huh. Silly little mistakes. Your character is named -11600566160. That's a lot harder to remember than Bartholomew or Cornelius or Foxtrot or Dan or whomever. So I just laugh at myself because I need to fix it. So enter name for character 1. I didn't realize that until just now. 96 of 3. That seems... Oops. That seems a little out of bounds there. Because I forgot to tell that print which variable it should assign, so it just took any old number. Alright, here we go. So, this should tell you something. No programmer is perfect. Refinements keep on occurring. Try to do the best you can, and eventually you'll put something together that actually works. At least, hopefully, with duct tape and WD-40 and all that other fun stuff. So let's say Walter. Okay. Now Theodore. Franklin. Very nice. So we've got our input. Now, how do we show it? Well, we can go back to the value of p, and then we print out while I is less than 4, and then more or less the same. Now we just print. Actually, because there's a new line in the string itself, it would make more sense simply to just have these two next to each other. Okay. P, was it temp name, temp health. Okay. And you know what? For giggles, I will also do that. Right. So that should work. Famous last words. Right. Again, a silly mistake. What did I forget to do? While I did use the I variable, I forgot to reset I to 0 for that next loop. Okay. So let's do this. Okay, Walter, Theodore, Franklin. Okay, so here we go. So this is the address for the first instance of our struct, because we've allocated 3 units of memory that incorporate the size of struct. So we can fit our name, our 25 character name, and the integer value of 100 So we can see the amount of memory required in order to host that information. So you see Walter 100, Theodore 100, Franklin 100. And then apparently I had another value here. But you know what? I've got it pretty good here. Okay. Oh, right. Okay. That's why. Okay. Mike, Charlie, Prentice. Ah, there you go. And again, you can see these are the addresses it decided to use, or this is the base address it decided to use. And yeah, so you can see the interval, you can see the size, difference rather between the memory addresses. Let's just see how big struct is. Let's see. So struct player. Okay. Okay. One more time. Size of struct player is 32 bytes. Given that we have 25 characters, 25 bytes are used there, and then we have a 4-byte integer. But then why is it 32 bytes? So with a struct, um, there is something that is known as padding, and that may need to be done internally by the compiler, I believe, in order to do data alignment. Basically, you have memory aligned in such a way that you want to make sure that there are that each integer starts at a particular location interval. And if say you're occupying some data with some characters that might otherwise override that next closest interval prior to the end of the characters, it will then shift over to the next available interval. So it could be a couple of bytes offset. So you want to make sure that instead you do that. Let's try again. Just swap the places of those variables. It's still 32. Okay. So 25 plus 4, but it will still... That's something that I'd like to hear from someone in the comments. If anyone has any insight as to why the struct is still 32 when I understand the character array is 25, and the integer itself is probably most likely 4, and it's still occupying 32 bytes. That could be because of the struct itself. Anyway, I just wanted to do some exploration. This has gone on quite a bit longer than I had anticipated, but that's okay. I had a lot of fun. I hope anyone watching did as well, and we'll see you again soon.